Hello there. Welcome back. Recently, we have been talking about uniform motion, that is, motion with constant velocity. But what if velocity is not constant and it's changing? Well, that's where acceleration comes in. Acceleration is present anytime we have non-uniform motion, which is motion with changing velocity. In this video, we will understand acceleration. We'll start with defining it and look at some of its properties. And we'll see what acceleration looks like in equations and in graphs. So what's a common example of motion where the velocity is changing? Let me take the example of you getting in your car in your driveway, starting it up and starting to move it. So here's your driveway that let's assume is straight, and here's your car, here's the steering wheel, and here you are. You get in your car, you start it, and you start moving towards the right to get going. Now, what would a motion diagram of this car look like? Well, it might look something like this. Initially, let's say your car was here. We're back to the particle model now. And a time interval later, it's over here. The same time interval later, it's moved more because you're starting it and speeding it up to get to your cruising speed. And so it goes over here, and let's say it goes over here. And as always, a motion diagram is complete only with the timestamp numbers below it. So let me add those over here. Now, to better understand this motion, let's see what the graph of this motion would look like. In particular, the velocity time graph is the one I'm going to start with. So this car is moving in the x direction towards the right, and it's moving in the positive x direction. So the velocity Vx is going to be positive. And so if I plotted velocity in the y-axis and time on the x-axis, my velocity started at 0, the car was at rest, and as time went on, the car was speeding up. So the velocity was increasing with time, let's say like this. So I've got Vx here, and I got time t over here. So this is different from the uniform motion graphs we were looking at, which had constant velocity, so the velocity plot was flat or horizontal. Now you might remember that for a uniform motion, let me just switch back to uniform motion for a second, there was a graph that looked similar to that, but it was not the velocity time graph, it was the position time graph. And it had a straight line because the slope everywhere was the same, which is what led to a constant velocity. And you might remember that in a position time graph, the slope was the velocity. Well, it turns out that by analogy, the slope in a velocity time graph is nothing but the acceleration. And acceleration in physics is written as lowercase a. And the slope was simply the rate of change of whatever was plotted on the y-axis. So velocity was rate of change of position, and acceleration is defined as the rate of change of velocity. And if I take two points here, and if I want to get the slope of this graph, as we've discussed before, the slope is the rise divided by the run. Let me just repeat it here for the sake of completion, that acceleration is the slope in a velocity time graph. And so acceleration, let's call it AX for acceleration in the x direction, which is what we have in this case, is simply the slope, which is the rise, or the rise is change in velocity from this value to this value. So that's delta Vx, change in the x velocity, divided by the run, which is the change in time, or time duration, which is delta t. So here we have the equation definition of acceleration. I'm going to delete the uniform motion analogies I used because they're not really relevant to this discussion directly, other than to show you the analogy. between the two. So from this equation, we can see that acceleration is a vector. I have a vector in change in velocity, and when I divide that by a scalar, I still get a vector. So that's an important point to note. Acceleration is a vector. And let's also discuss what the standard units of acceleration would be. Writing this equation again here and focusing on the units, I've got change in velocity, which is measured in meters per second, and I divide that by a time duration, which is seconds. And when you divide meters per second by second, I can rearrange this to say this is meters per second times 1/second, which gives me meters per second squared. And that's the standard unit of acceleration in SI units. One other point I want to make here quickly. Acceleration is the rate of change of velocity. What we're dealing with here is a velocity that's changing because the speed is changing. But what if the car was turning at cruise control? So you got the same speed, but you got the car going in a circular direction at the same speed. Do we have acceleration then? Well, the speed is not changing, but the direction is still changing. And when we have change in direction or change in speed or both, we have a change in velocity. And every time we have a change in velocity, we have an acceleration. We will study the kinds of acceleration that deal with change in direction later. For now, we're going to stay focused on acceleration in a one-dimensional motion where the motion is along a straight line. So that can only happen when there's a change in speed. So we'll stick to that for now, but you do need to remember that acceleration is not change in speed, but it's change in velocity, which means either speed or direction or both can change. And there's one more important point about acceleration I want to make. In our common language, when we say we are accelerating, we think of increasing speed or speeding up. And when we're slowing down, we prefer to use the word decelerate. While all that is correct in common language, that's not the case in physics. In physics, acceleration is all we've got. Anytime we have a change in velocity, it's an acceleration. So acceleration can imply speeding up. It can imply slowing down. It can imply a change in direction. It could imply any of those, and we will see in future videos examples of all of that. But I just wanted to emphasize right now that all of those things, speeding up, slowing down, changing direction, are all acceleration in physics. Okay, finally, to complete our discussion here, let's just see what the acceleration time graph and position time graph for this motion looks like. So here I'm plotting my acceleration time graph. So on the x-axis, I still have time. On the y-axis, I've got acceleration in the x direction. And in this case, since acceleration is the slope of the velocity time graph, and we got a straight line here, a straight line has the same slope everywhere. So in this example, I've got constant acceleration. Moreover, it's a positive slope, so it's a positive acceleration. And so that would look something like this. A positive constant acceleration would be a flat line above the x-axis. And then the position time graph would look like this. I've got position x along the y-axis. I've got time t along the x-axis. And let's say I started at the origin and my velocity initially was 0. I was at rest. So the slope here needs to be pretty flat. And then the velocity, which is the slope in a position time graph, keeps increasing with time, which means this graph needs to get steeper and steeper and steeper as I go. So it might look like this. And we can see that the slope at the beginning is just a flat line, which corresponds to the 0 velocity. The slope over here is tangent to the curve, so it would look something like that. So I've got an intermediate velocity, and then the slope over here is like this, so I've got even a higher velocity. So a changing slope in a position time graph is what's a clue that we have changing velocity and hence we have acceleration. So in this slice of physics, you got a good introduction to acceleration. Acceleration corresponds to changing velocity or non-uniform motion. We defined acceleration and we looked at some of its properties. We saw that acceleration is the slope in a velocity time graph, which meant that acceleration is the rate of change of velocity, just like velocity is the rate of change of position. Then we noted that acceleration is a vector, and as a vector it has magnitude and direction, and the units of acceleration in the standard international units are meters per second squared. Thanks for watching.